to the right. Okay, we have a high purity, but high contamination also. And if the threshold is a low value, then it is the other effect. The other way of seeing this is the precision recall curve. The precision, if you remember, is here, the fraction of predicted positives that are actually positives. And the recall is the fraction of actual positives that are predicted positives. So in this case, a random classifier also generates a curve here as a diagonal of the square.
Sorry?
See.
I am confused with the difference between accuracy and precision.
The difference? Accuracy, this one?
Accuracy versus the precision.
Precision is the number of true positives divided the number of true positives plus false positives. That is, the number of true positives divided the total number of predicted positives. Okay, that is the precision. And then the accuracy is the total number of events that are correctly classified. That is, true positives plus true negatives divided the total number of observations. Okay?
Okay.
These are different measures or different metrics which are used to quantify the performance of a method. Another measure, for example, is the area under this curve, which is called the area under the curve, or AUC, which is a value between 0 and 1. Okay, if the area under the curve is near to 1, then the classifier is very good. And if this area is nearly 1/2, 0.5, then the classifier is not doing very well. It is actually equivalent to a random classifier. Okay. So in our case, we have to decide if a given detection in the difference image, imagine that you have a new image, which is the difference image, and you run, for example, a sextractor there. Okay, you identify spots in the image, which can be positive or negative. If we, in the new image we have a transient event, then it is supposed to be positive, right? Well, and we have to decide if this detection is an actual transient event or just an artifact in the image. Then we have 4 different different methods, and for each one of these methods we can try different machine learning methods. So for each one of these, we tried, for example, random forests, k-nearest neighbors, and support vector machines. Okay, and we compare the performance of all these combinations. The problem is that before the detection of kilonovas, or even after the detection of the kilonova, we do not have a large data set for training of our algorithm. So we have to make injections on images that simulate the occurrence of transient events. Okay, so this is what we did. We used a set of images of the sky that are considered reference images, and we injected uh, simulating transient events. Okay, then the task is to use these injections to train an intelligent agent. When I say intelligent agent, I mean a machine learning program, okay? To train a program that is able to identify a transient event in a new image. So we can construct a set of images with injections to train the model, and another set of images with another set of injections to test the model. This is a basic procedure of machine learning methods. We have to train with a data set, and we have to test with a data set where we also know the result. Is that right?
Yeah, but for example, in the case of the kilonova, we only have one spectra or one image, no?
Yes, that's the problem. That's why we need to simulate images. In other case, for example, the case of the cats on images. We want to train an algorithm that is able to identify cats on images, on photos, for example. Then we construct a set of images with cats that also contains images without cats. And we use this data set to train a model. Okay? Then we construct a new set of new images with and without cats. And we use the trained model to test if it is able to identify the images that have cats. Okay? And with this procedure, we can have a metric of how well the classifier is doing. And once we know that our classifier is doing well, then we can apply it to a new image. Is it more clear?
Yep.
More or less? Okay, so in this case, the problem, as Jonathan said, is that we have just one observation. So we need to make simulations or injections of transit event on different images. Doing this, we have, for example, after the difference image analysis, from the set of injections, a set that are true sources, yes, true sources, a set that are artifacts that are identified by our methods but are not part of the injections, and a set that are missed injections. These are the true positives. These are the false negatives. Okay, we should have identified this, but we did not. These are the false negatives, and the artifacts are the false positives. Okay? Artifacts are false positives, true sources are true positives, and missed sources are false negatives. Okay? So after the machine learning, the KNN, the random forest, or the support vector machine, we have real detections and the so-called bogus detections, which are detections from the machine learning which are not actually transient events, which in this case are injected. Okay, so from the combination of the difference image analysis and the machine learning, we also have a new classification where we have distinguished between false negatives, true positives, false positives, and true negatives. This is just a scheme of the procedure, and we can compare difference image alone, machine learning plus difference image, and compare the performance of the different methods. For example, here we compare using this metric 1 minus the area under the curve, right? For the 4 methods and for the 4 machine learning methods. So since this is 1 minus the area under the curve, if this number is close to 0, it is a better method. Okay. So we use reference images that are real data and reference images that are simulated data. And we compare in the 2 cases the performance of the algorithm. Using this kind of analysis, we can decide which method is the best to identify transient events. Of course, once we obtain the output of the machine learning procedure, we have to go and make a detailed observation of that object, right? But the advantage is that machine learning methods allow us to have a much smaller sample of spots in the sky to observe, right? And these are the precision recall curves for the different methods. This is the case for support vector machines, and this is the case for random forests. So it is considering the training and the testing data sets, it is possible to analyze how well each combination of methods is doing. And this is the F1 score, which is a similar way to analyze the same thing. We have the 3 machine learning methods for each one of the 4 difference image analysis procedures. So with this, we can see which one is better, or which one has a larger spread using the data set. So the next step is to analyze different types of reference images and different types of injections. So we can consider, for example, how well the methods do for different magnitudes of the injections. Of course, if the injection is not so bright, then it is easier to lose it on the noise from the background image.
Marcelo?
Sí.
What means the circle in this plot?
Yes, we have here, this is the case for the real images. So it's the single value of the F1 score for a data set made with real images, which would be the reference images. So we were here analyzing different scenarios, considering simulated backgrounds, real backgrounds, different machine learning techniques, and different image analysis. So the idea here is that this toolkit of the machine learning and difference image allow us to find the best possible method to program into the pipeline to automatically detect reals and separate bogus events. Sadly, the answer is that there is not absolutely clear which one method is always better. And that is a problem which happens frequently in machine learning, that there is not a method that ensures to be the best method in all the cases. So it is not magic, okay? So we can analyze, for example, the importance of the different features in order to make the classification. This is the so-called feature importance ranking, okay? Which in this case we have for the support vector machine at the left, and then for the random forest at the right. With this, we can, for example, eliminate some of the features obtained from the image. These are features that are the output of the extractor program from the difference image. So we can select a small group of features to make a fast classification, for example, or to lessen the noise in the classification. So to end, I would say that anticipation is very important in many aspects. And given the fact that new gravitational wave observatories are coming, and that we need to make a rapid response to gravitational wave alerts to search for the optical counterparts, then we need to be prepared. So, I mean, we need to anticipate the needs of this new area of astronomy, which is the gravitational wave astronomy. The funny thing is that some years ago, we talked about gravitational wave experiments when we talk about, for example, LIGO or Virgo. But now, the astronomical community talk about gravitational wave observatories because they are truly observatories. This is a new window to the universe, and comparing these multi-messenger signals, we can learn a lot about the astrophysical properties of many events. Well, I finish here. If you have questions.
Yes, I have a couple of questions. I don't know if Jonathan have questions too.
Yeah, I have some questions.
Go on.
So you already responded almost of my questions during your talk. Was an interesting talk about these interesting objects. One of my questions is, so you are using Torus only to search or to look electromagnetic counterpart of gravitational waves?
Yes, as a part of the Torus collaboration, my main work is on the pipeline, on the automatic reduction of the images and the detection using machine learning of real and bogus events. However, the collaboration has access to several telescopes, including the two larger telescopes in Argentina, which are not so large compared to the ones in Chile. One is 2 meters and the other one is one and a half meter. And we also have access to Gemini and some smaller telescopes. And the Taurus telescope, which is something like 1 meter of diameter, we'll have the first light hopefully in the next months.
Okay.
People are trying to make this happen during the summer because winter in the Puna is very harsh, as you can imagine.
Yeah, because the magnitude, the limit magnitude is 21, 22 for this telescope.
Yes, actually, we have not filters. So this limiting magnitude is of white light.
Okay, okay. Because they are comparable with another, at the moment, is comparable with another telescopes that are looking for gravitational waves. Because usually the candidates for these events are around 20, 22 more or less, depends of the brightness. And my other question is regarding the methods that you later that explained later. Um, how do you choose one of the methods, or you can use all at the same time?
Well, in the work I explained, we compared these three different methods. There are many more methods that could be used. The problem is there is a theorem called the non-free lunch theorem in computer science, which says that there is no a single method that performs better for all the problems. That means that for each problem, we have to find the best method. It can be a different method for each problem. It is even possible that there is a method that performs better and we have not thought about. So the strategy is to propose several methods. This is very empirical, right? To propose several methods, apply the metrics for the performance of the different methods, and find out which one makes better the classification of real and bogus events. Does it answer your question?
Yeah, because I heard before in the gravitational waves use the hot pants. I'm not pretty sure about the others, but yeah, that was pretty good.
Yeah, the hot pants is an implementation of the Allard-Lupton difference imaging. I'm not sure if it has incorporated in the last versions a machine learning classifier. I think it does not.
Yeah.
But hot pants, I think, is not about machine learning, but about the difference imaging.
Okay. Okay. Thank you for your answers.
Yeah. Also, I mean, there is a combination of the two things: the difference imaging and the machine learning. And the task is to put these two procedures in the pipeline. So even it is possible that the pipeline could choose what combination of difference imaging and machine learning to use, depending on the characteristic of the observations. For example, the signal to noise ratio, the colors of the detections, I don't know, the height in the sky, the how crowded the field is. I mean, many factors that could affect the performance of the different methods differently.
Okay, great. Thank you.
Okay, I also have a couple of questions. First is of the when you talk about torus as a survey, in the sense of the torus of galaxy survey, do you observe a new part of the sky? I don't know if you mentioned already. If you already mentioned.
Yeah, there are two strategies. When you are looking for transient events in the following up of alerts for gravitational waves, then you have to compare to a reference. This reference image can be taken previously to the new image or even after the new image. since we know that kilonovas fade out in a matter of days, then it is safe to take a reference image, for example, some months after the new image. So they have to be separated in time for enough days. Because it is possible that we have not the reference image catalog for all the sky that we need at the moment of making a new observation. And in fact, when we made the searches for the counterpart of the event 170817, which was the kilonova, we made the observations for the reference image a couple of months after the observation of the transient event, because we did not have a previous reference image. Was that your question?
But if you don't have a reference image to do the rest, okay. I understand. Well, another question is, can you repeat what mean the F1 score?
The F1?
Yes.
Yeah, sure. F1 is, the thing is, it is a good thing to have a high precision and a high sensitivity. But most of the times, it is not easy to have both. Okay, so F1 is just another measurement for the metric of the performance of the method. That is the harmonic mean of the precision and sensitivity. Precision and sensitivity are just numbers, right? Which we can obtain for a given threshold and training and testing data sets. And the harmonic mean is twice the product divided by the sum of these two metrics, the precision and the sensitivity.
But
2 times precision times sensitivity divided the sum of precision and sensitivity. That is the harmonic mean. And that calculation corresponds to the F1 score. Sometimes the different scores are more sensitive to different things. For example, the balance between the two classes on the training data set, or specific characteristic of the different architectures, or so on. In general, it is advisable to have several scores, not just one. Not just, for example, the area under the curve, or the F1 score, or the accuracy, but a combination of them.
How you select a good F1 score?
How you, sorry?
Select a good F1 score.
A good F1 score?
Hmm?
I don't get your question, but you given a data set for training and testing, you can compute an F1 score.
No, voy a apuntarlo en español para que se entienda. ¿Cómo puedo seleccionar un buen F1 score? Tiene que ser cercano a 1, tiene que ser, si yo estoy comparando distintos F1 scores, ¿cómo puedo decir que este es bueno y este es malo?
Okay. Well, the ideal F1 score is 1,
Okay.
right? And a very bad F1 score is 0. So the range of the S1 score is between 0 and 1. But you do not choose the F1 score. You compute the F1 score for a given threshold. So you have a balance between the things that you lost. Sometimes you're more interested in a pure sample, and sometimes you're more interested in sample that it's not very contaminated. For example, for the case of the search for transient events, what do we want? We want a set of candidate objects that are very good candidates, or we want a set of candidate objects that include cases which are not very good candidates. We have two situations here. So the decision is made in terms of the availability of the instruments. If we have, for example, a very limited time frame to observe, then we need a small sample of candidates. And so we need very good candidates. But the problem with this is that the real event may have been identified by the machine learning algorithm with a low probability. I mean, not so high probability. So we, if we keep only the best candidates, we increase the risk of losing the right candidate. Okay, and in order to lesser the risk of losing the right candidate, we need to increase the size of the sample, including more candidates that are not very good candidates. So we need to observe a lot more number of galaxies. So the decision of the threshold depends on many factors, which are practical. Okay,
Okay.
it's an empirical decision. But for each decision, we can obtain an F1 score to decide in how well are we doing with this choice. Is it clear?
Okay. Yes. So I choose a threshold, and this mean an F1 score.
Yes.
Okay.
For different thresholds, you have different F1 scores.
Yes.
If you change your threshold in a reasonable region, then the F1 scores doesn't change so much. So here we need another metric or another criteria to make the choice of the threshold.
Okay, and my last question is about the end of the talk in the ranking of the features. Why you use different features if you are comparing the methods? Would not the comparison be more fair if they have the same features?
Yes. Once you have chosen the right features, then you use the same set of features always. But in our study, since we could make variations of the injections and the difference imaging and the machine learning, we could compare the importance of the different features. The problem is that some methods lose performance when the number of parameters is high. So if it is possible to clean the parameter space, eliminating the features that do not contribute to the classification, then the algorithms will perform better. But once we have decided which features to use, then we keep that set of features and use always the same set.
No,
I
for
don't
what?
know if I understand correctly your question.
So for both methods, you use the same features.
No, in our work, but you have to take into account that this work is using simulations to analyze the performance of the different combinations of machine learning techniques and different image techniques. If you have this, if you implement this in production, that is in a working pipeline, which is trying to detect on real time for a real case, then you're not changing the set of features. You use always the same set. Okay, so there are different situations. The problem here is that we do not have many observations of kilonovas. We have just one. So we have to make injections and simulations. Okay.
Okay.
I feel that I am not answering your question, but I am not sure.
No, sí, las diferentes features son porque ocupan inyecciones al haber pocos datos reales, por así decirlo, ¿o no?
Yes.
Yes. Well, I don't have more question. I don't know if Jonathan have another one. If not,
No.
no. Well, thank you very much, Marcelo. It's a very good talk. And well, if we have a new question arise at the day, I think maybe we can send by email.
Yes, of course. Of course. We have the PDF of the talk, which is not the final version. If you want, I can send you this version, which is more detailed.
Yes,
Final.
please, of course.
Okay.
Well, thank you very much, Marcelo. See you.
You're welcome. I hope it was useful for you.
Yes.
Yeah, a lot.
Very
I'm
interesting.
glad.
Thank you, Marcelo. Have a good day. Ciao,
Thank you.
Mauricio.
Ciao,
Bye
ciao.
bye.